Hi, and to all those who have been following my Merchant Navy How-To series, welcome back. In this video, we are going to continue completing the calculations necessary to plot our position from the stars. If you haven't already watched it, please make sure you watch part 1 first. So let's get started. Much the same as with most celestial calculations, we first need to obtain the Greenwich hour angle, and subsequently the local hour angle of our chosen celestial bodies. So taking our nautical almanac, and turning to the appropriate daily page for the 18th of October 2016, we can read off the values of the Greenwich hour angle in declination for Venus at 8 o'clock, or 2000. As you can see, the Greenwich hour angle is 89 degrees, 28.9 minutes, and we have a declination of south 21 degrees, 22.8 minutes. We also look at the bottom of the Venus column, where we will find the V and D correction values, negative 0.7 and 0.7 respectively, which we'll make a note of on our pro forma. Next, we turn to the yellow coloured increment and corrections pages at the back of the almanac. Finding the table for 45 minutes, we can read off the increment value for 45 minutes and 0 seconds from the planet column, which is 11 degrees and 15.0 minutes. We then obtain our values for the V and D correction from the same table, which are both 0.5 minutes. In the case of the V correction, it was negative, so we also name the correction as negative. When we add these together, we obtain our correct Greenwich hour angle of 100 degrees, 43.4 minutes, and our actual declination of south 21 degrees, 23.3 minutes. To obtain our local hour angle, we need to correct for longitude. To do this, we add or subtract our estimated longitude from the calculated Greenwich hour angle figure. If we are west of Greenwich, as in this case, we subtract the longitude, and if we were east, we would add it. This gives us a local hour angle of 55 degrees, 43.4 minutes. The next step is to calculate our altitude, which if you look on the back of my pro forma, or page 2 if you didn't print double-sided, you'll see some formulas and an explanation of each. These formulas are intended to be used in a single action with a scientific calculator. Using the formula, we simply substitute the values for each. Note that we enter all values as positive numbers, and different calculators have different ways of accepting degrees and minute values. You'll notice that in the middle of the formula is a plus or minus symbol. This changes dependent upon whether our latitude and declination are both the same hemisphere or different hemispheres. By this I mean if both our latitude and declination were north or both south, then we have to add here. If one is north and one is south, then we subtract here. Therefore, as our latitude is north and our declination is south, we subtract, which will give us the answer of 13 degrees, 20.7 minutes, which we inserted into the calculated altitude box on the pro forma. Next, we have to calculate the azimuth, and subsequently the true bearing of Venus. For those who have followed my earlier videos covering calculating the gyro error, you'll notice the formula here is the same. When we are entering our LHA, please take note that it is always a negative value. Also note that when we are entering our latitude and declination, if it is north, then we enter it as a positive value, and if it is south, we enter it as a negative value. When we do this, our calculator should throw out a number of 52.3, which we now need to convert to true. The first step is to name it correctly. Consulting the table on the back of the pro forma, we can see that where the LHA is between 0 and 180, and our answer is positive, we name it southwest. We can now turn back to our pro forma and insert this on it. However, before doing so, it's more useful to convert it to a true bearing. As it's southwest, we add it to 180, which gives us a true bearing of 232.3 degrees. Now let's move on to our first star, Nunki, as I believe it is pronounced, although I could be wrong. We start off as we did before, except instead of the GHA of the star, we use the GHA of Aries, which is what all stars are referenced to. If we look in our almanac on the relevant daily page, we should see the Greenwich hour angle at 8 p.m. or 2000 is 327 degrees, 44.0 minutes. We can also save some time here, as this figure will be the same for Alkaid, and fill in its box as well. We now need the sidereal hour angle and declination of our star. These are given on the rightmost column of the table on the first page of each set of days. So we simply have to find our star in the list and make a note of the values. In case they are not visible too clearly on your screen resolution, the SHA is 75 degrees, 55.7 minutes, and the declination is south 26 degrees, 16.4 minutes. As we are dealing with a star, there are no separate V or D corrections to be applied. Therefore, we only need to add the increment for the minutes and seconds. So we turn to the yellow increment and correction pages at the back of the almanac, and on the table for 48 minutes, we read off the value for 48 minutes and 0 seconds, which is 12 degrees, 2.0 minutes. We can now add these together, which will give us the Greenwich hour angle of Nunki of 415 degrees, 41.7 minutes. We then adjust this for our longitude, as we did before. Because we are west, we subtract our longitude, giving us a local hour angle of 370 degrees, 41.2 minutes. As is quite common when working with stars, an LHA of 370 degrees, 41.2 minutes isn't possible, as it's a complete circle which only covers 360 degrees. And a value of 370 means we've done a complete round and then continued on. Leaving it as it is won't affect the calculation from a mathematical point of view, but to make it easier for us later, we simply subtract 360 degrees, giving us the correct local hour angle of 10 degrees, 41.2 minutes. The same would apply if our LHA was less than 0 degrees. We simply add 360. When working with positions where the longitude value is high, you may have to subtract or add 360 multiple times to get back within the range of 0 to 360. As there was no correction for our declination, our actual declination is what was written in the almanac, south 26 degrees, 16.4 minutes. When we put these figures into the formula on the back of our proforma, we obtain a calculated altitude of 28 degrees, 53.1 minutes. And when we do the same for the azimuth, we get south 10.9 west, which equates to 190.9 degrees true. Now, I'm not going to show the working for Alkaid, as the process is exactly the same. So if you want to work it out yourself, please pause here. Otherwise, trust me when I say its calculated altitude is 26 degrees, 2.7 minutes, and its true bearing is 313.4 degrees. We've now done the hardest and most time-consuming part, but before we can get down to plotting our position lines, we need to make some corrections to our sextant altitudes we obtained for the bodies. Firstly, we have the index error. This is the error which we know exists on the sextant, either due to it being dropped or a design flaw. The index error for your particular sextant should be known before you start your observations. If your sextant had an error which is considered to be off the arc, then we add our index error to our sextant altitude. If the index error is considered to be on the arc, then we subtract our index error from the sextant altitude. After we have done this, the resulting figure is named the observed altitude. As it doesn't make any difference to our process, the index error of the sextant I used was 0, therefore the observed altitude is the same. Dip is the correction we apply for our height of eye to account for the difference between observations at sea level and where we are standing on our ship. To do this, we take our height of eye and turn to table A2 at the very front of the British Admiralty Nautical Almanac. It's also on the convenient detachable card that you're probably using as a bookmark. On the right of this table is the dip column, which contains corrections for a variety of heights in both metres and feet. 20 metres conveniently is one of the rows in the table, giving a correction value of 7.9. If our height of eye is not in the table, then we would need to interpolate between the two surrounding values to get the correction to apply. The good news is that providing you use the same location to do all your star sites, you only really need to do this step once per ship. When using this table, also make sure you use the meter values and not feet. Assumed altitude is our observed altitude corrected for dip, so let's enter that value now. Just to clarify, I have called it assumed altitude. However, it is referred to as apparent altitude in the British Nautical Almanac and also elsewhere. We now have a bunch of other corrections to possibly apply. The TC box is intended to hold any corrections required due to refraction for the body. We get this by consulting either table A2, which is altitude correction tables for 10 to 90 degrees, or A3, which is altitude correction tables 0 to 10 degrees, depending on what our assumed altitude is. For our planet Venus, we had an assumed altitude of 13 degrees, 16.3 minutes. Looking at table A2, we obtain the correction value of negative 4.0 minutes. You do not need to interpolate for these values. You've probably noticed that right next to that is another column. If we are using Mars, Venus or the Moon, then we have an additional correction to apply for these bodies, which we insert into the AC box on our proforma. As we're using Venus and it's the 18th of October, we can see that for all assumed altitudes between 0 and 60 degrees, the correction we have to apply is plus 0.1 minutes, which will now stick into our proforma. The ULC box is intended for corrections necessary if we were using the Moon, which we're not, so we will leave it empty. Next comes the last correction, which is for non-standard conditions. To obtain this correction, we need to know the air pressure and temperature at the time of the observation. We then look into the graph at the top of this table for pressure and temperature and see which column or zone we fall within. Luckily for us, we are in zone G, so the correction to be applied is 0. If we are in a non-standard condition, then we interpolate for our assumed altitude in the table and obtain the value relating to the column whose zone we are within. So when we put it all together, we obtain a true altitude for Venus of 13 degrees 20.4 minutes. To then calculate our intercept, we simply subtract the calculated altitude from our true altitude, which gives us negative 0.3. I'll leave you to work out the intercept for our stars yourself. If you want to do it, you can pause now. Otherwise, here's the correct values that you should have. That's it with all the maths. All that remains now is to plot our position. So join me in the next video when we'll complete our example by plotting our position using our radar plotting sheet. I'll also explain how to plot the position on a chart and graph paper as well. To make sure you get notified when I post videos in the Merchant Navy How To series, remember to hit subscribe. And if you found this video helpful, click that like button. Until next time, safe sailing.